Welcome to the lecture on this passive compensation. We were discussing the numerical examples. So, this is the sixth numerical examples. A 3-phase 3-wire delta connected balanced load of ZL equal to 3.0 per unit plus 1.0 per unit has an input AC line voltage of 415 volt 50 hertz AC supply and a base impedance of 8.25 ohm per phase. So, it is to be realized as a unity power factor load on the AC supply system using shunt connected lossless passive element, and calculate the supply line current, compensator current, the value of compensating element, its kVA rating and equivalent per phase resistance of the compensated load. Well, this is the circuit of the this problem, schematic diagram and perform waveform. So, we have a 3-phase supply and we have a this typically a balanced load connected of reactive load across the 3-phase line, and then we have a here the compensator, and these are the typical waveform after estimating that and after the designing of it like. So, let us discuss that given a supply voltage of 415 volt at 50 hertz, 3-phase load of 3 plus 1 per unit J per unit with base impedance of 4.15 ohm. So, from this we can calculate the load resistance by utilizing this typically this 4 into 3, this become 24.75 and load reactance typically of 4.15 into 1, that is 8.2. So, the load admittance YL is equal to 1 upon ZL and GL minus JBL. So, it becomes like 0.0364 minus J 0.12 mho. So, supply current after the compensation will be IS root 3 VSGL. So, it will be 26.13 ampere. Because of the balance symmetrical operation, the current in all the 3 phase after compensation will be 26.13 ampere only. For unity power factor operation of the compensators and compensators are to be connected in parallel to all the load branches. For UPF operation, so BL should be equal to minus BC and that is 0.0121 mho, and compensator phase current will be that Vs into BL. So, here the is connected across line to line because of delta connection. So, it will be 415 into 0.0121 that comes 5.03 ampere, and all compensator branches share the equal compensator current like. So, the value of capacitor for power factor correction C equal to B C upon omega. So, it comes 38.58 microfarad, and compensator VA rating you can call it, it is for the all 3 phases it comes like 3 VIC. So, it will be 3 into 415 into 5.03. So, it becomes 6267 VR, it equivalent to like a 6.26 typically of VAR. The equivalent resistance of the compensator load is R equal 1 upon GL, and that your 27.5 ohm. Well, coming to the next problem, typically a problem number 7, a 3-phase 3-wire AC distribution system has a line voltage of 415 volt 50 hertz and feeder impedance of 2 ohm resistance and 2 ohm inductive reactance phase, after which a balanced delta connected load of 24 plus J18 ohms per phase is connected, and calculate the voltage drop across the source impedance, voltage across the load. If shunt compensator consisting of a lossless passive element is used to raise the voltage as the same as the input voltage as shown in figure, calculate the supply line current, compensator current, the value of compensator element and its kVA rating. Coming to solution of this problem, given that the supply phase voltage is 415 by root 3, that is 239.6 volt, and frequency of supply of 50 hertz, and delta connected load of ZL equal to 24.J18 ohms per phase. The source impedance is at RS plus JS 2 plus J2 ohm, and the star equivalent of the load will be ZLY will be equal to ZL delta by 3. So, it becomes 24.J18 divided by 3, and that comes 8 plus J6 ohms per phase. The total impedance at the circuit equivalent star connection, including the source impedance and equivalent star, will be ZT equal to ZS plus ZLY, that will be your 10 plus J8, and that magnitude of you can call it of impedance is your 12.806 ohm. So, the load line current before compensation will be I Vs upon Gt, and that is 230, that is a phase voltage 415 by root 3 that is equivalent to 39.6 divided by 12.806, that is the impedance, and value comes of this 18.71 ampere, and the average voltage drop across the source impedance after the compensation will be Is Vs Vz S old equal to Is old into Zs, and that comes typically after multiplication of this, it comes 52.919 volt, and voltage across the load before the compensation is your now Vz old as where Is old into Z del y by root into root 3. So, it comes 324.06 in place of 415. So, you can call it like now, because it is a lagging power factor load and you have a reasonable source impedance or feeder impedance, and that is the reason this voltage reduces from 415 to 324.061 volt. So, load where the now we can convert the load admittance per phase, I mean as a load conductance in equivalent star GLY plus JBLY, that is 1 upon ZLY, and it comes to equal to 0.06 minus J 0.06 mho, and the load power factor can be made unity by connecting a susceptance in parallel to this equivalent to that will be BPF for power factor correction minus BLY, and will be 0.06 mho. So, let the susceptance of the value BCV mho is to be connected in parallel to the load to raise the voltage equal to the input voltage for voltage regulation, 0 voltage regulation, VL equal to Vs, and the basic equation to regulate the load voltage equal to the voltage is as VL magnitude should be equal to the Vs magnitude, and VL magnitude we can calculate of course by finding the current and then the multiplication of the your let us say load admittance, load impedance along with the compensator which we have already put it like. So, that will be Vs upon the total impedance, I mean the source impedance plus the impedance of the load along with the your you can call it the compensator impedance multiplied the impedance of the load along with the compensator. So, that solving this we will get BCV equal to XS plus minus under root XS square minus XS square RS square into 2 RS GLY RS square GLY square and XS square GLY square and divide by XS square RS square. So, substituting the value of XS equal to 2 RS equal to 2 and GLY 0.08 and considering minus sign in plus minus for lower value of the compensator, the value of BCV is as BCV equal to 0.123 mho, and total susceptance for power factor correction and voltage regulation now BTV will be equal to BCV plus BPF, that is 0.183 mho, and the now the supply line current will be keeping the value in this source impedance, and then total it comes like 239 point the putting the value of all these elements, it comes 35.152 ampere, and susceptance to be connected line to line for power factor correction, that is BD equal to BT by 3, and that is a 0.061 mho. Well, after the compensation the load line voltage is 415 and the compensator current are to be VL line voltage into the BD compensator you can call it susceptance, and that is 415 into 0.661. So, current is 25.315. The value of capacitor for power factor correction and voltage regulation is CD equal to BT upon 3 omega, and it comes 194.169 microfarad, and kV rating of the compensator is now 3 VL square into BD, and by keeping 3 into 415 square into 0.661 that comes 31,517.17 MVA, it comes the 31.517 kVA as the compensator kVA rating. So, this completes this problem. So, coming to another numerical examples, number 8, a 3-phase 3-wire unbalanced delta connected load which have outlets across the line AB ZAB equal to 5 plus 2 J 2.0 per unit and ZB 4.0 plus J 1.2 ohm per unit and ZC A 7.J2 per unit has an input line voltage of 415 50 Hz AC supply and base impedance of 5.25 ohm per phase, and it is to be realized as a balanced unity power factor load on 3-phase supply system using a shunt compensator consisting lossless element. Calculate the A supply line current, B the value of compensator element, C compensator current, and D its kVA rating, and E equivalent per phase resistance of the compensated load, because after compensation it should behave as a unity power factor load on the balanced load as a supply system. So, coming to the solution of this, so this is the typically the network. You can just see that we have an unbalanced load connected in delta, and then we have a compensator element for across all three, you can call it delta connected load with the three elements. That compensator is also connected in delta across the each branch, and compensator is responsible not for power factor correction and balancing the load also across the supply. And these are of course after getting the design the waveform are plotted, and you can see the supply currents are in phase with the supply voltage, and typically all other waveform of compensator currents are also given here. So, coming to the solution of this problem, given that supply voltage of Vs equal to 415 and frequency of 50 Hz, a 3-phase 3-wire unbalanced delta connected load of ZAB equal to 5.0 plus J2 per unit and ZB 4.0 plus J1.2 per unit and ZCH 7.7 plus J2 per unit with a base impedance of 5.25 ohms per phase. We can find out actual impedance of the all three by multiplying the per unit value with the base impedance. So, load impedance comes ZLAB comes 26.25 plus J 10.5 ohm and ZLBC it comes 21 plus J 6.3 ohm and ZLCA 36.75 plus J 10.5 ohm, and load admittances come YLB equal to 0.0328 minus J 0.013 mho and ZBC 0.0437 minus J 0.0131 mho and this YLCA 0.0252 minus J 0.0072 mho. So, total load conductance here which is sum of all three conductance as it comes GLT equal to 0.1017 after putting the value of all three conductance of the load, and supply line current after the compensation from the relation it will come ISA equal to Vs into ZLT by root 3 into at a angle of 0, it comes at typically I times this, and similarly your B phase will be 120 degree apart and ISC will be or 240 degree apart, and the magnitude of current we can calculate ISA equal to Vs into GLT by root 3 into at the angle of 0, it comes 24.36 at the angle 0 and ISB 24.36 ampere at the angle of 120 degree, ISC 26.36 which is equal to the all three balance current at the phase angle of 240 degree. So, that cause the balance 3 phase channel current at unity power factor in phase with the supply voltage, and we can find out the compensator susceptances that we say be applying the relation which we derived in the previous lecture. So, minus BLAB plus GLA CA minus GLC divided by root 3. Similarly, for VCB minus VLB in bracket GLAB minus GLC divided by root 3 and BLCA equal to VLCA plus GLBC minus GLB by root 3, and then of course, putting the value of all these we get the compensator susceptances BCA 0.024 mho, BC 0.0175 mho and BCCA 0.0134 mho, and the value of elements comes from there. If we calculate the value of first element is the capacitor, so it is a BCC by omega, so it comes 7.639 microfarad, and across the BC it comes as a capacitance, so it is a BC by omega, so 55.83 microfarad, and for CCA it also another capacitor that is a BC omega, so that is also typically comes from the previous value, it comes 42.81 microfarad. So, that is the compensator value for all three, and compensator phase current we can find out Vs into the this susceptances. So, it comes 1.011 8 ampere and ICB second compensator across the BC line comes BS CCB and it comes 7.2 8 ampere and ICA for VS CCBA. So, it comes 5.5817 ampere, and compensator VA rating comes like voltage which is equal across, and we can take a mode of all these three currents. So, it comes typically 5.75 kVA, and equivalent delta connected resistance in ohms of this we can find out Re equal to 3 divided by GLT and it comes 29.50 ohm per phase like So, that provide the typically you can call it like not only power factor correction, but load balancing what we demonstrated in this example. Coming to another example, typically example number 9, a 3-phase AC supply system has a line voltage of 415 volt at 50 Hz and the feeder impedance of 0.5 ohm resistance per phase and 3 ohms inductive reactance per phase, after which a unbalanced delta connected load with ZAB equal to 15 ohm, ZBC of 20 ohm and ZCJ 25 ohms is connected. To calculate the A voltage drop across the source impedance, the voltage across the B voltage across the load, if shunt compensator consisting of lossless passive element is used to balance this load and to realize it as a unity power factor load. Moreover, calculate the supply line current, the value of compensator element, compensator current and its KVA rating and equivalent per phase resistance of the compensated load after the compensation. So, this is the typically the circuit configuration, that we have a source impedance which is equal for all three phases in series, and we have an unbalanced load which the value of two conductance and another is susceptance, and then we have a compensator element for across the all these delta connected load. So, after proper design and getting the value, this waveform are plotted and you can clearly see that the power factor is corrected to typically to unity, like after the compensation. Coming to the solution, given that supply voltage of 415 volt, frequency of 50 hertz and 3 phase 3 wire unbalanced delta connected load of your ZL AB across the line AB is 15 ohm and ZBC 20 ohms and ZLC is your J 25 ohm with the feeder impedance of 0.5 ohms resistance per phase and 3 ohm inductive reactance per phase, that comes equal to 0.0 plus J 3 ohm, and load admittance we calculate 1 upon Z, it comes LB 0.0667 mho and YLB 0.0500 mho and YLC minus J 0.04 mho. The equivalent star connected conductance and resistance after compensation, we have to add all conductance as a relation we derive GLT equal to GLAB plus GLBC GLC. So, it comes 0.1167 and RLT comes as 8.57 ohm, and the total impedance in the star connected equivalent load, like in balanced load, is along with the source impedance, and this resistance comes like 0.074 plus J 3, and it can be converted into the typically polar coordinate 9.55 at the angle 18.30 degree ohms. Then the source current after the compensation, which is equal to IS equal to Vs upon root 3 to get the phase voltage into ZLTY in star connection. So, that comes around 25.06 at the angle 18.30 degree ampere, and voltage drop across the source impedance will be ISZS. So, that comes your 76.26 volt, and voltage across the load comes VLT IS into RLT, that is 214 9.0 ohm. That is the line voltage comes 372.29 in place of typically 415. So, because of the source impedance, the voltage across the load reduces, like even we put this load as a balanced load, resistive load across the this typically line like. Now, coming to B part, the supply current after the compensation ISA equal to Vs upon root 3 ZLY at the angle of minus 18.23. Similarly, for all three currents will balance. So, ISA will be 25.06 at the angle of minus 18.30 degree ampere, and similarly for B phase 25.06 ampere at the angle of minus 138.30 degree, and ISC will be 25.06 ampere at the angle of 101.70 ampere, and the compensator susceptances will be from these relation minus BLB plus GLA minus GLBC by root 3. So, this relation we have derived. So, putting the value, so it comes the compensator value BC equal to 0.0385 mho and BCAB will be minus 0.0289 and BCCA is 0.034 mho, and value of compensator element will be capacitance for line across AB will be your BCA by omega. So, it comes 122.55 microfarad. Similarly, for your CAB is equal to typically as a your inductance, that is 110.14 millihenry, and similarly capacitor across the line CA will be your 96.69 typically 5 microfarad, and the compensator phase current will be, of course, we can find out Vs into CV, that comes 11.98 ampere. For the BC it comes like 15.97 ampere, and for CA it comes again 12.60 ampere, and compensator V rating we can find out V into absolute value of all the current, it comes 16.832 kVA R, because it is all reactive elements there, and the equivalent delta connected load of compensator load will be R equivalent 3 by GLT into that comes about 25.71 of equivalent star connected load like. So, that completes the ninth problem. Now, we come to the solution. Typically, another example of 10th numerical example, a 3-phase AC supply system, a line voltage of 415 and 50 hertz and feeder impedance of 0.5 ohms and 2.5 ohms inductive reactance, after which unbalanced delta connected load ZAB 15 ohm, ZBC 20 ohm and ZCA of 25 ohms is connected. Calculate a voltage drop across the source impedance. The voltage across the load if shunt compensator consisting lossless passive element is used to supply these loads and to raise the voltage at the same as the 415 volt, and also calculate the supply line current, the value of compensator element, compensator currents and its kVA rating as equivalent per phase resistance of the compensator load after this 0 voltage regulation like in that case. Well, this is the typically again network. We have a balanced source impedance, which is responsible to reduce the voltage, but we have to regulate the 0 for the 0 voltage regulation, and we have a typically this unbalanced load, and putting the compensator element we should be able to balance the load and then we should be able to regulate the voltage. So, we have to find out the the compensator elements value in susceptances, which is lossless element in terms of these elements like. So, given that supply voltage of 415 volt, frequency of 50 hertz and a 3-phase 3-wire unbalanced delta connected load with the impedance of across line of AB is 15 ohm, line BC is 20 ohm and line CA is 25 ohm with the feeder source impedance of 0.5 ohms resistance and 2.5 ohm inductive reactance per phase, and load admittances will be corresponding to the reciprocal of this YLAB will be 1 upon ZLAB equal will comes around 0.067 mho, and similarly YLB comes 0.05 mho and YLCA comes 0.04 mho. So, this compensator system of load balancing and power factor correction comes that we derive the relation for 3-wire system in terms of these load susceptance and conductance, and after putting value it comes like a BLCAB 1 0.058 and BLCB 1 0.05 mho and SA 0. So, we can call it according to star equivalent conductance after the load balancing and power factor correction, it comes GLT sum of the all 3 load conductance, it comes 0.1567 mho, and star connector equivalent resistance after load balancing and power factor comes RLT equal to 1 upon GLT, that comes 6.383 ohm like. And let the susceptance value of PC mho to be connected in parallel to a star equivalent load, that is GLY equal to GLT as per the phase representation to raise the load voltage equal to the your input voltage. So, basic equation to regulate the load voltage to equal to the input voltage is that load voltage magnitude should be source voltage, and we can find out the load voltage in terms of source impedance and the load admittance along with the compensator element, which is shown this in equation, and the derivation solving this equation which we derive many times, the value of VC becomes xs plus minus under root xs square plus xs square plus r square into 2 rs gly plus rs square gly square plus xs square gly square and divided by xs square rs square. So, substituting the value of xs equal to 2.5 rs 0.5 and gly 0.01567 and considering the minus sign in plus minus for lower value of compensator, the value of BCV is as BCV equal to 0.0695 mho, and that will be JXCV equal to 1 upon JV, that comes minus J 14.38 ohm, and ZLC along with RLT, and that this admittance comes around 5.3328 ohm minus 2.3666 ohm, and which comes 5834 at the angle of 23.935 ohm, and supply line current after the compensations will be IS equal to, because now load voltage is the same as the source voltage. So, it comes VSA upon ZLT into root 3 at the angle of 0, it comes 239 after putting the value of this both elements. So, it comes 41.06 at the angle of 23.935. It means the typically the load have to be made, this current have to be made leading, only then you will get the 0 voltage regulation, like that's meaning of that like. So, we can now calculate the voltage drop across the source impedance is IS ZS. So, it comes putting the value of IS and ZS, we get this 104.7, and voltage across the load comes like now IS into ZLT, that comes same as the supply voltage 415 by root 3, that is nothing but 239.6 phase after the voltage regulation, and supply line currents after compensation come ISA VL upon ZLT in root 3. So, at the angle of 23.93 it comes 41.06 at the angle of 23.93 and other two phases will be at just exactly 120 degree apart with the same magnitude. So, susceptance for voltage regulation will be as BV delta equal to BCV by 3 and it will be 0.23 mho, and total susceptance for load balancing and voltage regulation we can calculate some of the this and which are used earlier for load balancing, and we get the 3 value typically 0.0174 across line B, and across line BC it comes 0.036 mho, and across line C it comes 0.0136 mho. Value of element compensator elements comes CAB equal to BCB omega, that is come 55.39 microfarad, and for across your line AB it comes 122.78 ohm, and line C it comes around 43.13 microfarad, and compensator phase current will be this line voltage multiplied this compensator element, it comes 7.2216, and then for line BC it comes 16 ampere and line C it comes 5.62 ohm, and compensator VA rating is the absolute sum of all these three current multiplied the voltage. So, it comes like your 11.974 kVA, and equivalent delta connected resistive load of the compensator, that is Req is a 3 upon GLT, it comes 19.14 ohm. Well, coming to the another example, example number 11, a 3 phase 3 wire unbalanced isolated neutral star connected load with the ZA equal to 5.0 plus J2 per unit and ZB 4.0 plus J 1.2 per unit and ZC 6 plus J 2 per unit, has an input line voltage of 415 volt 50 hertz AC supply and base impedance of 5.3 ohms per phase, and is to be realized as a balanced unity power factor load on the 3 phase supply system using a shunt compensator consisting of lossless element. So, calculate the supply line current, compensator current, value of compensator element, its kV rating and E equivalent per phase resistance of the compensated load. So, these are typically the network that we have unbalanced isolated star connected load with the compensator, which is responsible for maintaining the unity power factor and balance current in the supply system. And after designing, getting the value, these waveform are plotted, which give you the typically the unity power factor current in phase with the your supply supply voltage. So, coming to the solution, given that the supply voltage Vs equal to 415 volt and frequency of 50 hertz, a 3 phase 3 wire unbalanced delta connected load with the value of ZL equal to 5.0 plus J2 per unit and ZLB 4 per unit plus J 1.2 per unit and ZLC 6 plus JU per unit with a base impedance of 5.3 ohm per phase, and getting a load impedance in star connection with the value of per unit multiplying. So, it comes ZA equal to 26.5 plus J 10.6 and ZB 21.2 ohm plus J 6.36 ohm and ZC 31.8 plus J 10.6 ohm. Load admittance will be just reciprocal of them. So, that will be like typically 0.035 mho at the angle of minus 21.80 degree. Similarly, for your B phase it will be your 0.0452 at the mho at the angle of minus 16.67, and your C phase will be your 0.0298 at the angle of minus 18.43 mho. And we can find out load admittance in equivalent delta connection by converging delta to star connection by these formula star to delta conversion, and we get these three mohs virtually for the line admittances, and from this we can find out the conductance of all three lines from these three first elements, and that comes to equivalent to a 0.0 typically of your 342 mho, which comes after the typically of load balancing. And we can find out line current after compensation, that is ISA Vs into GLT by root 3, and all three will be balanced. So, we can put the value of this Vs GLT 1 by root 3, it comes 8.1847 at the angle of 0. Similarly, for B phase at the angle of 120 degree and I the angle of your 240 degree, and compensator susceptances from this relation we can find out typically in the mho, putting the value of this, and it comes typically you can call it the capacitance. I mean, if you calculate 10.4 AB across the AB it comes 10.09 microfarad and BC it comes 19.622 microfarad, and your line CA it comes 7.77 microfarad, and total compensator phase current I mean Vs into these you can call it the your susceptances. So, it comes 1.3161 ampere, and for line BC it comes 2.5582 ampere, and line CA it comes 1.0131 ampere. The compensator VA rating comes as absolute value of these current multiply voltage, so it comes to 2028.3 and VR rating, that is 2.02 kVR, and equivalent data connected load comes RE equal to 3 upon GLT, and that comes 87.82 ohms like. Well, coming to typically the example number example 12, this is on 4 wire system, a 3 phase 4 wire system for 15 volt 50 hertz AC supply system, has a single phase load 7.5 kilowatt load, unity power factor load connected across line to neutral, and it is required to eliminate the neutral current using a shunt compensator consisting of lossless passive element, and calculate the supply line current, the value of compensator element and compensator current and its kVA rating. So, here you can see the network here. I mean, the load is connected between A and neutral, and by putting the compensator elements across the two line, we can eliminate this neutral current. This can be made 0, and after getting the value, it is shown here, and typically the neutral current is eliminated completely here in this case. So, this is the only case of only eliminating the neutral current. You may have a reasonable solution. So, here we have come with the unique solution. Given that supply voltage is given for 15 by root 3, because it is a star connected load. So, we have to find out per phase, you can call it the phase voltage. So, that comes to 39.6 volt, frequency 50 hertz, and single phase load of 7.5 kilowatt unity power factor load connected across the line to neutral. So, we can find out the load impedance Vs square by P, and putting the value we can get this ohmic value 7.65 ohm, and the load admittance per phase comes of reciprocal of 0.13 mho. It requires two substances across the other two phases and neutral terminal to eliminate the neutral current, and substance across the loaded to correct the power factor to unity of single phase load. So, however, the load is a unity power factor load, hence only two substance for neutral current compensation are required. So, the supply line current after the compensation, that is for A phase VSB GL upon at the angle, and ISB at the VS GL upon root 3 at the 50, and ISC VS GL upon root 3. So, putting the value of this, we get typically the current in A phase 31.30, that is the typically the load current, and this is for B phase 18.067 at angle of 150 degree, and C phase 18.067 at typically at 210 degree, because those are, and compensator substances we can find out from this relation, which we derived already earlier, and we can find out BCA is 0, because we do not need, it is already resistive load, and BCB typically minus 0.754 mho, and BCA 0.0 plus 0.075 mho, and value of elements will be across, you have to put across the typically across the B to neutral is a inductance. So, that comes 4.22 millihenry, and across the capacitance across the line C to ground is 240.09, and that cause the neutral current to go to 0. I mean, like neutral current flows are the two phases. The compensator, of course, we can find out the element here in A phase 0, B phase we get the value for corresponding to this per phase voltage multiplied this substance, and C phase we getting this, and compensator element we can take absolute value multiplied this voltage, it comes 8.66 kVA. So, this example give you idea that neutral current can be compensated with lossless passive element even for single phase pure resistive load. Like coming to another example of 13, a 3 phase 4 wire 15 volt 50 hertz AC supply system has a single phase 25 kVA 0.8 lagging power factor load connected across line to neutral terminal, and if it is required to eliminate neutral current using a shunt compensator consisting of lossless passive element, calculate A supply line current, B the value of compensator element, and C compensator current, and D is kVA rating. So, this is typical here. The example, I mean, with neutral load is connected between A phase and neutral, that is a inductive load, and then of course, with this compensator value we have to make unity, and after that we have to use two other compensator to make this neutral current 0. So, that is required to realize it as a unity power factor load on the supply and making neutral current 0. So, coming to the solution part, given that supply voltage is your 415 by root 3, that 239.6 frequency of supply 50 hertz, and a single phase load of 25 kVA 0.8 lagging power factor load connected across line to neutral, and the load your impedance is your 1.9166 plus J1234, that comes 2.29 ohm at the angle of 36.87 degree, and the load admittance will be reciprocal of this. So, it comes 0.0 435 at the angle of minus 36.87 mho. It requires two susceptance, the other two phases and the neutral to eliminate the neutral current and susceptance across the load phase to make unity perfect of single phase load. So, this comes like a typically the all the three phase current like of the supply, and it comes after putting the value, it comes 80 typically 86.477 ampere at the angle of 0, and similarly for B phase 48.1953 at the angle of 150 degree, and IC at the 48.19 typically at the angle of 240 like, and compensator susceptances will be from this relation. I mean it will be your capacitance value will be 831.74 microfarad, and inductance for line CB will be your 15.1 millihenry, and line C it will be 640.12 microfarad, and compensator current putting the value it comes like a similarly 48.19 ampere at the angle of 150 degree. Similarly for C phase it comes 48.19 at the angle of 240 degree. So, compensator V rating V into absolute value of the current will be 38,091 6.068 VR or 38.09 kVR. Another example of 4-wire system. So, example number 14, a 3-phase 4-wire shunt compensator consisting of lossless passive element is employed at 415 volt 50 hertz supply system to provide load balancing and unity power factor of a single phase load of 24 kilowatt unity power factor load connected across line and neutral as shown typically here, only resistive load. Calculate the value of compensator element, compensator current and supply line current and its kV rating. So, here we are typically providing the load balancing and power factor correction also in spite of single phase line to neutral load. So, coming to the solution, that given the supply voltage of phase voltage from line voltage 415 by root 3 to 36.9 volt and frequency of 50 hertz, a single phase load of 24 kilowatt at unity power factor connected across the line A to neutral, and we can find out the load virtually impedance that comes to 2.392 ohm because it is a resistive load because of unity power factor, and we can find out admittance here. So, the conductance part only there 0.18, and but the susceptance part is 0 because there is no reactive power in the load. So, it requires two sets of susceptances, one is star connected, another in delta connected sets across the line to eliminate the neutral, and compensator star connected substance for neutral current and power factor correction. From this derived relation we can get the value, and here for A phase it comes 0 because it is a resistive load. So, there is no need of any compensator element. Across the BC it comes 0.241 ohm, and for CA it comes 0.241 ohm, and value of element is star connected compensator comes from this value, a 0 microfarad for obviously for A phase, for B phase inductance of 13.18 micro millihenry, and capacitance across the C to ground it will be neutral, it will be 768.291 microfarad, and compensator which is delta connected substances from these relations which we derive in the last class, we can put the value and we get the of course these all substances, and the value of delta connected element as a capacitor 512.194 microfarad, inductance across the typically here 19.7282 millihenry, and from this we can find out the star connected compensator element currents from these relation, and the star connected compensator for A phase have a 0 current because there is no compensator element, and for B and C it comes 57.831 ohm. Similarly, for delta connected compensator for line B C it is 0, and for other two it comes 60.78 equal currents like, and now we can find out typically the supply current after the compensation from this relation, it comes 33.389, and with the angle of minus 120 degree and plus 120 degree for balanced load at unity power factor on the supply system, and the compensator element we can find out with the absolute current multiply the phase voltage, and from this for star connected and for delta connected it comes after addition 83.138 kVA. So, in this case what you have done, we have taken a load balancing, we have taken a power factor correction, as well as neutral current elimination. So, all three functions we did with this compensator. Coming to the typically a numerical example number 15, a 3-phase 4-wire shunt compensator consisting of lossless passive element is used at 415 volt 50 hertz supply system to provide load balancing and power factor correction of single phase load of 25 kVA 0.8 lagging power factor load connected across line to neutral and calculate a supply line current, the value of compensator element and compensator current and its kVA rating to provide the load balancing, and power factor correction means to realize the unity power factor load. And this is the circuit of the configuration that we have a typically here, for realizing it as a 5 elements, otherwise the solution will not be unique. So, we already discussed earlier when we were discussing the condition. So, we take a 5 elements, 5 elements virtually delta 3 and star connection only 2 elements. So, it becomes then unique solution because there are 5 elements and there are 5 equations like and putting the value of course, in this relation, given that the supply voltage is VSP 415 by root 3 and frequency of supply 50 Hz and single phase load of 25 kVA 0.8 lagging power factor connected across line to neutral of A phase. So, we can find out load impedance from this relation. It comes 2.29 at the angle of 36.87 ohm and load admittance one reciprocal of this 0.435 at the angle of minus 36.87 ohm. It requires two set of susceptances, one again star, another in delta across the line to eliminate the neutral current and load balancing, and typically after supply current after compensation is a balance current. It comes 29 point after putting the value 29.114 at the angle of 0, then minus 120 degree and plus 120 degree as a balance current, and compensator is star connected substance for neutral current and power factor correction. The value after keeping the relation, these comes typically the capacitance comes 831.74 microfarad, and for inductor for line BY it comes 15.83 millihenry, and line C it comes 640.12 microfarad. Similarly, compensator for keeping in this relation for delta connected capacitance, the value comes of typically line AB it comes like a 426.85 microfarad, and the inductance for line CA it comes 23.74 millihenry, and the compensator is star connected phase current. Putting the value this it comes 62.61 ampere, and for line CB it comes 48.18 ampere, and line C it comes 48.184 ampere, and the compensator delta connected putting the value. So, it comes for line AB 55.65 ampere, and for BC it is typically 0 because there is no element, and line CA it is typically 55.65 ampere, and the compensator VA rating the phase voltage multiplied the 3 phase current for star equivalent and the line voltage multiplied the absolute value of all the 3 line current of compensator. So, putting the value of this it comes like a typically 84.28 kVAr compensator rating like. Coming to another example, number 16, in 4-wire system, a 3-phase 4-wire unbalanced load has an impedance of ZA equal to 5.0 plus J2 ohm connected between phase A to neutral terminal with the input line voltage of 415 volt AC supply system and a base impedance 5.3 ohms per phase, and it to be realized as a balanced 3-phase unity power factor load on the 3-phase supply system using a shunt compensator consisting lossless passive element. Calculate A the value of compensator element, supply B supply line current, C compensator current, D kVA rating, and E equivalent per phase of the compensator load. So, this is the network. Here again we are taking only 5 element, all 3 typically all 3 star element, in delta we are taking 2 element. So, one current of delta element will be 0 like also, and after getting the solution getting the value, these waveform are drawn from typically putting the value in the circuit network. So, coming to the solution, giving that supply voltage of 415 volt by root 3, that is a phase voltage 239 because it is a star network, and frequency of supply system 50 hertz, a single phase impedance of the load is 5.0 and plus J2 per unit connected between phase A to neutral with a base impedance of 5.3 ohm per phase. So, we can find out the load impedance and then the load admittance, and require 2 set of star connected compensator, one in star connection, another delta connection, and compensator we have considered for star connection for the neutral current compensation and power factor correction, and the value for star connected compensator comes about the typically a value of this, and from this we can find out the capacitance for A phase 41.43 microfarad and inductance for B 169.5 millihenry, and for phase C it comes 59.78 microfarad. And delta connected compensator we have of course typically compensator for 2, so it comes like a line AB it comes 0.125 mho and BC it 0 and your C8 0.0152 mho, and getting the value of this in element capacitance come 39.85 microfarad, and line C8 comes to 54.64, and of course, there is no element across the your BC line. So, capacitor star connected phase current, by putting the value of your susceptances and voltage, we get the three phase current 3.15 ampere. Then for B phase it comes 4.5 ohm, at C phase it comes 4.5, and for delta of course, we get the one we get the 0, other 5.18 and then 5.18 ampere, and then we can get all three phase supply current, which is a balance current, putting all these values. So, we get the balance current 2.598 ohm at the angle of 0, then minus 12 degree, and for C phase at a plus 12 degree, and compensator VA rating of course, the phase voltage, the current of star connected compensator, line voltage, and delta connected current compensator, and it comes addition of both, it is a 7.02 kVR a compensator, and equivalent per phase resistance in star connection, that comes to be like a sum of all the conductance by 3, and it comes typically in resistance at 92.308 ohm. So, in coming to another example of 17, a 3 phase 4 wire unbalanced load of Z A equal to 3.0 ohm plus J 1 per unit, and Z B 4 per unit plus J 2 per unit, and Z C 6.1.2 per unit, has a line to line voltage of 415 volts AC supply and base impedance of 5.3 per phase, and it is realized as a 3 phase balanced unity power factor load on the 3 phase supply system using a shunt compensator considering lossless passive element, and calculate the value of compensator element and the equivalent per phase resistance of the compensated load. And this is the network. Again, we have a 5 elements here. For star connection, we all 6 element, we have a 3 delta and 3 star connection, and for eliminating the neutral current and power factor correction and balancing the load like also. So, that is typically the solution. Coming to supply voltage of phase voltage of 415 by root 3, that is 239, and then taking a impedance of this unbalanced load ZLA, ZLB, ZLC in per unit, and multiply the base impedance, we get the actual ohmic impedance, and from that we get the admittances, and after that we get the, it requires 2 set of susceptances, one in star connection, another in delta connection across the line to eliminate the neutral current and load balancing, and compensator in star connected we consider all the 3 elements, and we get the typical value of these susceptances, and then we are getting a capacitance for A phase 73.83 microfarad, line B to neutral we get 11.063 microfarad, and C we get 53.79 microfarad, and of course, delta connected compensator we connect only typically the these relation, we get the value of this, and we get the capacitance value 23.237 microfarad, and for BC we get 9.23 microfarad, and C we get typically inductance 315.158 milli, and equivalent per phase resistance after getting conductance equivalent divided by 3, with that we get equivalent to star, and resistance comes per phase equivalent in star connected mode is come 24.08 ohm. So, we provide the load balancing as well as neutral current elimination and unity power factor operation in that case. So, coming to another example 18, a 3 phase AC supply system have a line voltage of 415 volt at 50 hertz and feeder impedance 0.5 ohm resistance and 2.5 ohm inductive reactance, after which a unbalanced isolated star connected load having a Z equal to 12 ohm, Z B equal to 24 ohm, and Z C 33 ohm is connected. Calculate A, the voltage drop across the source impedance, the voltage across the load if shunt compensator consisting lossless passive element is used, and balance at unity power factor, and then raise the voltage same as the 415 volt in both the cases. So, we are having a power factor correction as well as load balancing, then power factor correction, and after that the voltage regulation same as the this. So, we have a typically a star connected load, and we have a like a 6 element of the compensator after the source impedance. So, we will be having a power factor correction, load balancing, and then after that we will have a voltage regulation. So, after getting all those relations, these are the typically after design we have plotted the waveform for the with those compensator values, and we come as a balanced load at unity power factor with the as well as voltage regulation also. So, coming to the solution, given that the supply voltage is line voltage 415 by root 3 is the phase voltage 239.6, 50 frequency of 50 hertz, and unbalanced isolated neutral star connector having a ZB, ZC connected this, and load admittance we can get from these impedances, and for perfect correction load balancing the neutral elimination, the star equivalent load conductance in a star configuration comes out for balance load, and where the equivalent resistance in the star connection comes 19.6364 ohm, and total impedance across the supply. Now, we can find out which is sum of the resistance plus the source impedance. So, it comes like a supply line current from which we can get. So, we can get the drop after the balancing, this voltage drop across 30.1052 volt, and voltage across the load impedance after the balancing comes only 231.87 in place of 239.6. So, it means this is around 8 volt is the drop in the source impedance, reduction in the 8 voltage, but the drop in the source impedance is much higher because of the angle difference like also. So, compensator star connected substance of for neutral current component and perfect correction. These are for your star connected compensator, and putting the value of this all elements of the load, we get the value of capacitance for A phase to ground neutral 25.52 microfarad, the inductance between B and neutral 92.2 millihenry, and C to neutral it comes 75.57 microfarad, and compensator for delta connected, I mean these are the typical derived relation, and putting the value of this we get the capacitance across line AB 51.04 ohm microfarad, and capacitance across the BC we get 17.01 microfarad, and line C typically CA it comes inductance 148.9 millihenry, and let the susceptance of value CV mho is connected across in parallel to the load to raise the voltage equivalent to VL equal to Vs, and these equations of course are derived per phase, a per phase equivalent star connected load, the load voltage. So, this relation we already have the phase typically the voltage across the load per phase voltage will be equal to the your supply voltage magnitude, both same for 0 voltage regulation. This is the typically the current calculation which is flowing in the line in star connected equivalent network multiplied the your load impedance along with the compensator, and from which we can get the compensator element for 0 voltage regulation in terms of typically the source impedance Rs and Xs as well as the load conductance and here the VCV. So, after putting the value of Xs equal to 2.5 Rs 0.5 and the GL of the load after the load balancing and perfect correction, and considering minus sign for lower value of compensator, it comes BCV 0.0138 mho and capacitance value comes 43.94 microfarad, and then we can find out the typically the load admittance after the voltage regulation and load impedance after the voltage regulation, ZLT comes 18.9424 ohm, and current in the supply comes after voltage regulation 12.644 ampere, and voltage across the source impedance comes 32.23 volt. However, the load voltage comes same to 39.6 because it is a 0 voltage regulation. So, it maintains same voltage as the source voltage after putting this compensator like or so. So, coming to another example 19, a 3 phase AC supply has a line voltage of 415 50 hertz and feeder impedance of 0.5 ohm resistance and 2.4 ohm inductive resistance, after which a balanced star connected load of Z equal to 24.J16 ohm per phase is connected, and calculate the voltage across the source impedance, voltage across the load if shunt compensator consisting of lossless passive element is used to raise the voltage same as input voltage, means 0 voltage regulation, and value of compensator element and compensator current and supply current and kV rating of the compensator. So, we have a source impedance which is balanced, but we have a here the typically a balanced load. So, purpose it have a unity power factor compensation of the load, and after that we have to raise the voltage, means 0 voltage regulation, we have to find out the solution, and this is the typical after getting solution with the element values, putting that we got the balance voltage for unity power factor as well as typically for voltage regulation. So, coming to the solution, given that the supply line voltage is 415 volt, hence the phase neutral voltage is 415 by root 3, that comes to 39.6 and frequency of 50 hertz, and unbalanced size and star connected load typically of comes here typically this connected load connected to feeder this, and load admittance comes this, and we can get a for load balancing the equivalent admittance in star connected, which comes load resistance 34.66 ohm. A set of star connected substance in parallel to the load is required for power factor correction, typically this susceptance, and then the voltage across the load impedance is ISZS 19.89, and voltage across the load comes after the load balancing is 225. So, there is a voltage reduction here from 239.6 to 225 because of source impedance. In spite the load is made balance, and after that a value of BCV for voltage regulation is connected in parallel to the load. So, that the load voltage and your source voltage is made equal like on. And getting the solution for voltage regulation, this we are keeping the magnitude of the load voltage equal to the source voltage, and this is the calculation of typically source current, and multiplied the impedance of the load along with the compensator. So, we get the compensator relation which we have discussed many times, and putting the value of this we get this typically the compensator value of typically for voltage regulation, then we add for all three for which have used for perfect and load balancing, and from this we get the compensator current value, admittance value, and we get the typically the load value. So, we are able to get supply current here after the compensation, and kV rating we get equivalent to 4.494 kVR like. So, coming to the problem number 20 as an example, a 3-phase AC supply system has a line voltage for 15 volt and a feeder impedance of 0.5 to 2.5 ohms inductive reactance, after which a unbalanced data connected load is connected ZAB, ZBC and ZCA, and if load is to realize a balanced unity power factor load with shunt compensator, using this calculate supply current, compensator current, and typically kV rating and power loss in the source impedance after the compensation. So, this is typically the unbalanced load data connected, source impedance there, and we are putting compensator typically for balancing this load. Coming to the solution of typically of this of supply voltage with the phase voltage, and we have a compensator 3-phase element. After this we got the conductance, and then for load balancing and unity power factor load we get the typically equivalent load resistance which have to be in star connected, and we get the load impedance, and then the typically the supply current, and we got the load voltage now 221, which is reduced because of source impedance. It's come 221.10 43 in place of 239. So, because of the source impedance is come, and line voltage we can find out it's only 382.96 in place of 415 volt, and compensator delta connect substance load balancing putting of this value we get the capacitance across the AB 61.69, DC CB we get of course 0 millihenry, there is no need, and another compensator 164.2 millihenry, and we get the typically compensator current and kV rating, absolute value of compensator, and line voltage. So, we get 6.82 kVR, and power loss in the source impedance from 3 ISC square RS. So, it comes 93.14 watt. So, with this these passive shunt and series compensator are considered as a better alternative for power quality improvement due to voltage and current based power quality mitigation. We are able to have a simple design, high reliability compared to other options of power quality improvement, especially in absence of harmonic voltage and current. It is considered to be beneficial to the designer, user, manufacturer and research engineer dealing with the power quality improvement in the distribution system such as furnaces, traction system, rural supply system, to balance consumer load, reduce the negative sequence voltage at the PCs, and to improve the power factor and to improve the voltage regulation. And these are the some of the references like typically, and thank you like